In this lesson, we'll talk about absolute extrema and relative extrema. First off, an absolute minimum is the smallest value that the function takes on an entire interval. The very smallest. And when I say the smallest value, I'm talking about a y value. The absolute minimum, the smallest value that the function can take, what it is it's simply a value x inside the interval so that the function value is smaller than any other function value on the interval. Similarly, the absolute maximum is when the function hits a value that is higher than any other value of the function on that interval. Sometimes we call these things extrema, and so it's a term that whenever you hear it's extrema. We just know we're talking about maximums and minimums. Here's a few pictures below to talk about when a max and a min may exist. In the first picture, notice that we have an absolute maxima on the right and an absolute minima here in the middle. And in this particular example, we're looking at a closed interval from -1 to 2. The minimum is at 0, 1, the maximum is at 2, 5. In the second picture, we're now looking at an open interval. Now, an open interval still has the same minimum. However, on the right, we can't call this the maximum because it's not a point on the function. That's one of the requirements for an absolute maximum, is that it needs to be a point on the function that's higher than all the other points. This is not a point on the function on an open interval, and you can't really find a highest point. You can find an upper bound on the points, but not an actual point that's higher than the rest. So this picture has no absolute maximum. In the final example, we're again on a closed interval, but this time we have something funny going on where the minimum was. This time it's a discontinuity, a removable discontinuity, but regardless, now we no longer have a minimum because we can't use this point. There is no point on the function that's smaller than the rest. But notice that there is a maximum. Long story short, as long as we have a closed interval and we have a continuous function, we always get a max and a min. That's what we see here with the extreme value theorem. If the function is continuous on a closed interval, then there is an absolute minimum and maximum every time. How do we find these values? To get us started, we need the concept of a relative maximum and a relative minimum. The relative maximum simply means look on a small region of the graph and find an absolute maximum of that small region. So a place where the function hits a maximum temporarily and then goes back down. The function may rise higher further on, but in that little area, this point is the highest point. We call this a relative maximum, and you may hear me use the term local maximum, which means the same thing. Similarly, we can talk about a relative minimum, and the relative minimum has the same idea, but it's a minimum instead of a maximum. To look at our ideas here, we've got the relative max, the relative min, and in the next image we have a relative max, which seems easy enough to work with, but there's no relative minimum. And then finally in the last picture we have a relative minimum, but this one's a little bit different. This is a sharp turn. We didn't ever have that the function was differentiable. That was one of the things that could break differentiability. Sharp turn could still be a relative minimum. With that said, if we think about this, everywhere where it hits a max or a min, it has a horizontal tangent line, or perhaps with the horizontal tangent lines there might be no derivative whatsoever. This is what we call a critical number. A critical number is a point where the derivative is either 0 or undefined. You might hear me call this a critical point or a critical value. They're all the same idea. We look at where the function has either the derivative being 0 or undefined. 0 or undefined. When this happens, here's what the theorem gives us. Our relative extrema will only occur at the critical numbers. All we have to do is find the critical numbers and then check, are these relative extrema? Now we've got different ways to do this, but this is the way that we'll set it up. Let's take a look at this first example. We're not going to find relative extrema just yet, that's the next lesson, but for right now, the absolute extrema. The absolute extrema of the function y equals 2x squared minus 8x on the interval from 0 to 6. Now I really don't have a great way to do this right now other than look at the picture, so let's just draw it. One thing I can do to quickly take an idea of this is just to set it equal to 0. If I set it equal to 0, factor out a 2x. I don't really need this in general. This is just a way to draw this picture and get a feel for it. If I factor it, set each term equal to 0, I get x equals 0 or x equals 4. Those are 2 points on the function, 0 and 4. We'll put 6 somewhere up here, and knowing that it's a parabola, I'm going to guess that it looks something like this. To find the absolute extrema, what I can see from my picture, this function is on the interval just from 0 to 6. So from what I can tell on my picture, it looks like the minimum occurs at one of the relative extrema, and the maximum occurs over here on the right. Since we think it happens at a relative extrema, let's find the critical numbers. If I take the derivative, that derivative is defined everywhere, so I'll set it equal to 0. I get 4x equals 8, so x equals 2 is a critical number. And looking at my picture, this is definitely a minimum. It's both the local minimum, just by the picture, and it's also the absolute minimum. With that said, I see that that's the minimum, and it looks like the maximum is at 6, so what we're going to do is we're going to check the endpoints. It does appear pretty obvious that it passes through 0, 0. We even got that a minute ago, but let's just make sure that that's not a place where the max is. We'll explain this a little bit more in the next slide. We'll also look at the relative extrema. So f of 2 is 2 times 2 squared minus 8 times 2. That's 8 minus 16 is negative 8. And then finally we think 6 is where the max is. So 2 times 6 squared minus 8 times 6, that is 24. The absolute maximum is at 6, 24, and the absolute minimum is at 2, negative 8. So we use the picture to get that. Let's get some more ideas from this. As it turns out, we found that the local max and the local min were good places where the absolute max or the absolute min could occur, and the other good places were at the endpoints. The strategy is, if we check every place where there could be a relative max or relative min by looking at the critical numbers, and we also look at the endpoints, that's enough to say these are where my global maximum and minimum occur. Here's your strategy for finding the absolute extrema. First, find the critical numbers. Look at all the critical numbers and simply say where is the derivative 0 or undefined. These are your critical numbers. And then we'll check f at the critical numbers and at the endpoints. That's it. And when I say f, I mean the original function. Once you found the critical numbers, erase the derivative from your mind. You no longer need it. Check the critical numbers and the endpoints. Plug them in the original function, and then here's what it is. The smallest is the min, the largest is the max. Easy enough. So critical numbers, endpoints, plug them in the function. Highest is the max, lowest is the min. We'll start out by finding the critical numbers. So f prime of x is 2 minus 3 times 2/3 x to the negative 1/3 using your power rule, which I'll rewrite that as 2 minus, the 3's are going to cancel. We have 2 and the x to the 1/3 I'll write in the denominator because of the negative power. First off, let's set it equal to 0. And when I set it equal to 0, I can start off by multiplying by the denominator, x to the 1/3, to clear that out. And I have 2x to the 1/3 minus 2 equals 0. Add 2 to both sides, and I get 2x to the 1/3 equals 2. So x to the 1/3 equals 1. Now the strategy to get rid of this 1/3 power, you can think of it either as just a power with a reciprocal that you'll raise to, or think of it as a cube root that you would normally erase with a cube power. Either way, we'll cube both sides, but reciprocal power is the general trick. And I get x equals 1. That's one critical point. From the derivative being 0, f prime equals 0. The other possibility is where the derivative is undefined, and that happened this time. Remember, this was the derivative. But x equals 0 is undefined here, isn't it? If I use 0, I get a 0 in the denominator. So x equals 0 is another critical point from f prime undefined. So remember, always check for 0 and undefined. Alright, the next step simply says plug in your critical values and your endpoints. Check them all. So when I plug in 1, I get 2 times 1 minus 3 times 1 to the 2/3. 1 to any power is still 1, so I get 2 minus 3 is negative 1. When I plug in 0, looks like all the terms go to 0, so that's simple enough. Negative 1. Now when I plug in negative 1, I got to think about this power a little bit. Remember, top is the power, bottom's the root. Top is the power, bottom's the root. So the power is a square. Negative 1 squared is 1. Then the root is a third. I'm going to take 1 and take the third root, or the cube root if you will. So I have negative 2. The cube root of 1 is 1, so it's just 3. I get negative 5. And then finally we'll plug in 2. So I have 2 times 2 minus 3 times 2 to the 2/3. Now I don't have an exact value for that, but it wouldn't be too complicated to approximate it. Looks like approximately negative 0.76. With that said, the highest is the max, the lowest is the min. The highest was actually 0 here. The absolute max is at 0, 0. And the absolute min was the lowest one, which looks like the negative 5. So that was at negative 1, negative 5. Next example. We've got x cubed minus 3x squared. So we'll start off with the derivative. This one's pretty easy. 3x squared minus 6x. That's all we got to do. Notice this is defined everywhere, so I do not have to check later where the derivative is undefined. If I set this equal to 0, I'll start out by factoring a 3x out. I get x minus 2. With that said, 3x equals 0, or x minus 2 equals 0, meaning I get 0 and 2 for my critical values. Now, there's one thing that I didn't mention earlier. Look at this question and look at the critical values that I just got. Negative 2 to 1 does contain 0. It does not contain 2. So let me just go back up right here and note. Each critical number in the interval is the key here. The interval has to have the critical numbers in it. We don't want to check values outside of the interval because if those are the absolute max or min, they don't count. They're outside the interval. With that said, this is outside the interval. We have one critical value and we have 2 endpoints. So plug them back again into the original function. Don't try the derivative, just plug them into the original function. We've got the endpoint We got the critical value that we found that was 0. And then we've got the other endpoint of 1. It looks like -8. This is 4, so -12. I get -20 at -2. I get 0 at 0, and I get 1 minus 3 is -2 at 1. The absolute maximum is at 0 again, 0. The absolute minimum is the -20, so -2, -20. Last example. This one involves a quotient. So when I take the derivative, I'm going to need the quotient rule. So here it is. Derivative of the top times the bottom minus the derivative of the bottom times the top, all divided by the bottom squared. I get 2x times x squared plus 3 minus 2x times x squared, all divided by x squared plus 3 squared. The first question is this undefined anywhere? Better said, is there a 0 in the denominator? No. No, there's not. X squared plus 3. X squared is always a positive value, or at least non-negative. If you take x squared and you add 3 to it, there is no way that that answer can be 0. It can't happen because x squared is always at least 0. This function is defined everywhere. With that said, we're going to set it equal to 0. So to do that, this is going to be the first time I ever simplify a quotient rule, because solving the equation would really help if I do. I get 2x cubed plus 6x minus 2x cubed divided by x squared plus 3 squared. Nice cancellation happens here. And so my final derivative, which I'm not going to write the equal sign here, is 6x over x squared plus 3 squared, but I'm going to set that equal to 0. Multiply by the denominator again. Doesn't make much of a difference here, it just disappears. So that crosses out. I get 6x equals 0. So finally my critical value is 0. Good. Alright, final step. Plug them all in. Plug in -1, which is an endpoint. Plug in 0, which is a critical value. And plug in 1, which is an endpoint. Alright, I get -1 squared over -1 squared plus 3. That's 1 over 1 plus 3 is 1/4. At 0, I get 0 squared over 0 squared plus 3. That just simplifies to 0. And at 1, looks like I'm going to get the same answer as I did for -1. As 1 squared and -1 squared are the same values. The absolute max, we have a choice this time, don't we? Anytime this happens, we simply just say one or the other. So it could be at -1 1/4 or 1 1/4. Either one can be called the absolute maximum. And then the absolute minimum happened at 0 0.